My goal today is to talk to you about pressing issues in the field of neuroscience, that is how to filter or threshold information in complex brain networks. So, as you may have noticed from the previous presentation, at a certain point we need to threshold on networks that we have estimated from the neuroimaging signal. And why it's like that? Because this is basically a more general problem. So the networks that you have, and especially the weights of the links of your networks, are not a physical quantity. So they are an estimation, because they are inferred by measuring some similarity between some experimentally recorded data. So it means that especially for the lowest weights, they can suffer for some statistical uncertainty or artificial connectivity due to third-party interactions in the data. So this is basically the reason why, especially in neuroscience, where your signal are often recorded by means of neuroimaging techniques in vivo, we need a way to threshold this, to prune the connections in your network, and also to binarize. So this is typically what you observe in the studies on brain networks. You have to binarize because we are not sure about the weight of the connection. Now the point is that to do that, there are many methods. So you can arbitrarily select the threshold, as you have seen in the previous presentation. There are some other methods that are more based on the distribution of the estimators that in some cases are known. So you can fix a statistical threshold and then come up with a filtered threshold network. But now the point is that once you do that, you can come out with networks with a different number of links, different number of connections. And this can be especially a problem, especially in the neuroscience community, because we often want to compare different brain networks, for example, compare different populations or different conditions. And of course, comparing two networks which have a completely different number of connections can pose some sub-problems. And why it's like that? Because you know the network properties basically depend on the density of the network themselves. That is the actual number of links divided by the total capacity of the network. So here, just take, for example, the global and local efficiency, which have been introduced before. And these are two well-known graph quantities that have been used to characterize complex networks. They have been introduced in 2001 by Latora and Marchiori. And they are basically, they can be considered basically as the equivalent of the inverse of the characteristic path length for the global efficiency. And local efficiency is the equivalent of the clustering coefficient. So on the left side, global efficiency quantify integration of information in the network. On the right side, local efficiency quantifies the segregation of information in your network. Now, as you can see, these plots show that depending on the network density, these quantities can vary a lot. And if you see here, for almost empty networks and also for almost full connected networks, basically these quantities, both of them cannot really distinguish between two antithetical configurations, that is to say random networks and lattice. So at this point you cannot really distinguish by using this metric if your network is random or not. So this is somewhat related to from a general perspective to theoretical information theory. Of course, here where everything is connected with everything, you don't have information because there is no really topological information, and you have the same condition for almost empty networks. If you have no links, there is no information. Okay. So the point is, which is the best connection density then to observe and to quantify the network properties of your networks? Of course, every one of you will say, well, it's something in the middle, but which is exactly the number of links that you could and you should use. And of course, this is not a trivial question in general, but we are somewhat lucky if we refer to the results that we observed in the last decade in the field of the network neuroscience. So if you do a very short review of the literature, you come up with basically two strong recurrent messages in the field of brain networks. That is to say, no matter which is the scale of your brain networks, but brain networks tend to exhibit two important characteristics. First of all, they are efficient, meaning that they tend to optimize integration and segregation of information, that is to say, high global and local efficiency if you want. And second, they tend to be economic, meaning that for brain networks, there is a price to pay for each connections to be established. So this price to pay, if you want, is the energy consumption, the metabolism, and the energy that you need to establish connections between two distant regions of the brain. And what they have found basically is that these brain networks also tend to be very sparse in order to diminish as much as possible this wiring cost. So what we did then is try to put mathematically this kind of generic information and try to derive an efficiency cost function that we call J, in which we basically quantify the global and local efficiency of the network with respect to the density of the network. Okay. And so basically the aim would be, would it be possible to find the optimal connection density that maximize this functional? And this is basically the expression of the formula that you would like to have. Now the point again that this is not trivial again, because global and local efficiency in general are very hard to compute, especially for large networks. Also there is, in general, they can change a lot according to the network topology. So finding an analytic expression of these for the optimal density rho can be problematic, but again it seems that we are lucky because we could refer to some, at least to two theoretical results that have been shown in the literature. That is to say, we know exactly we know the approximation of the clustering index of the shortest path length, at least for two well-known configurations, that is completely irregular lattices and completely random networks. So if you go into, you look in the previous literature from the Watson-Strogatz model, you know that you can have for very large network sizes, where n is the number of nodes, you can have an analytic approximation of the characteristic path length and clustering coefficient for regular lattices and random networks. So here is the expression, n is the network size, that is the number of nodes, and k is the average node degree. So I will not enter into the detail, but according to this approximation that I told you at the beginning of the talk, so you can consider global efficiencies as the inverse of the path length, and the local efficiency as basically the clustering index. It means that basically you can rewrite the efficiency cost function as a function of the number of nodes and your density. Okay, basically because the density is related to the average node degree. And what we got, this is the main first message of the talk, is that this is the optimal density that we obtain for regular lattices and random networks. And the first things to notice is that even if these two networks have a completely different topology, their optimal density is strikingly similar. So they both follow a power law with the number of nodes, so the optimal density scales with the inverse of the number of nodes of the network. And also the numerator here that you see that basically is the average node degree is very, very similar. It's almost can be approximated by 3. So what does it mean? This would mean that in general, at least for these two models, the optimal density would correspond to select an average node degree which is equal to 3. So very sparse networks. Okay. So what we did before, okay, we say this is a very ideal case, regular lattices, random networks, but let's see what happens when we move to more realistic network models like small world and scale-free network. And to do that, we perform some simulation to generate synthetic networks. So we generate synthetic networks by changing the size of the network and also by changing the density of the network. And to do that, we really move and explore the whole range of available density. And what we did is that we compute our J function, the efficiency cost function that you see in color in this background, and we pick the maximum of this function. And you can see the maximum of this function correspond to the blue square here. And if you try to fit the blue square here with a power law, you see that again we obtain a nice fit with the synthetic networks that we obtain. And again, you can see that the average node degree is interestingly very close to 3. We also move further in order to validate these results on real data. So what we did then is to take brain networks or connectomes, if you wish, obtained from different neuroimaging studies across different species. So we have connectomes derived from the zebrafish embryos, the mouse, monkey, the human being, and obtained from completely different neuroimaging techniques. So basically the aim was to find if this result could be generalized. So you see it. And also the connectomes that we obtained was derived according to different connectivity metrics. So we have Granger causality for calcium imaging data obtained in the zebrafish. We have a Pearson correlation for fMRI data and spectral coherence for EG and so on and so forth. But again, the main message is that this network, these connectomes, all exhibit a different network size. And what we have found by maximizing the function J is that again the optimal density tends to follow this power law. So really it seems that we could establish a general law at least for multiple neural systems, and again you can see that the average node degree tends to be close to 3. Just to be precise here, what we did is that from these original connectomes, they were fully connected and weighted. What we did is to simply select the strongest link, the first strongest link, then the first two strongest link, and then we basically with an increase in connectivity density threshold, we computed every time our efficiency cost function. We took the maximum and we selected the corresponding density. And you can see it in color. Okay, so this was, I mean, at least for us, it was really impressive because we were not expecting such a kind of general behavior, and we wanted anyway to have a sort of explanation. I mean, what happens at this specific optimal density? How did the networks do resemble? To what do resemble? How do they like? To what they are similar? And which are the properties that we can have at this specific optimal density? And to better have an explanation, an idea of what happens here, we just consider two very simple cases. Again, the lattices and random networks. And here we generated different synthetic networks according by varying the connection density and the network size. And we consider the global and local efficiency values. So you can see in red the local efficiency and in blue the global efficiency values. And you can see that the black lines here for both cases represented the values of our efficiency cost function. Now, the optimal density would correspond to the peak of each of the black lines. Okay, and what you can see is that if you put in a connection density that corresponds to the peak, you can see that basically this method that we call the efficiency cost optimization criteria, or ECO, if you wish, is able to give you automatically the sparsest density for which you are able to emphasize the intrinsic properties of those networks. That is to say, high local efficiency for lattices and high global efficiencies for random networks. So at this point, it seems something that was reassuring us, and it seems that this method was really able to give a plausible connection density. Now, to finally validate this criterion, what we did is that we asked the following question. So, is that ECO useful in practice, and how can we validate its usefulness? And of course, as you know, we still don't know which is the real structure of brain networks, so we cannot validate if we are able to recover the real structure of the brain networks because we don't know that. What we ask is to try to see if this method was able to better separate the properties of different brain conditions or different brain states. So what we did is we consider different neuroimaging studies. involving healthy and disease population. So we consider connectomes obtained from EEG, fMRI, MEG, and DTI for different kind of diseases. So we had stroke, coma, and epilepsy. Okay, and of course you have, according to the neuroimaging techniques that have been employed, you have a different number of nodes. And we applied our criterion in order to filter the network, and we quantified the network properties of these brain connectivity patterns according to different graph quantities at three topological scales. So you have large topological scale, global and local efficiency, intermediate topological scale, so we evaluate the community partition and the modularity, and also at the smallest topological scale, we consider the node degrees and the betweenness. So the idea, again, was to compare these graph quantities between the two conditions, healthy and disease, and see if ECO is able to better separate these different conditions. In order to do that, we compare the results we obtain with ECO with other akin methods that are based on a similar principle, like the maximum spanning tree, the planar maximally filtered graph, and a sort of hybrid that we call MST plus ECO, in which you basically start from a backbone you obtain by applying the MST approach, and then you start the strongest links in order to obtain the same optimal density that you obtain with ECO, that is to say, an average node degree K equal to 3. So the next will be my final slide, in which you basically we basically report the result that you obtain for different neuroimaging connectomes, and also on the x-axis you have the different graph quantities that have been employed. In color, you have the results, the distance between the two conditions, healthy and disease, that you obtain by using the MST, the planar maximally filtered graph, the hybrid method I just introduced before, and the ECO criterion I just introduced before. And as you can see from this picture, the results that we obtain with ECO almost always outperform significantly the other existing methods. There are, of course, few exceptions, like, for example, if you consider the local efficiency, in which the hybrid version of ECO and ECO are basically almost the same. So there is no significant decrease, because the statistical variability and the standard deviation is very high. So in this condition, we cannot say that ECO is outperforming MST plus ECO, but at least there is no significant decrease. So I think that this is my last slide, and just a few conclusions about this procedure. Of course, the ECO criterion is not the definite answer to the problem of threshold in brain networks in neuroscience, but it has some advantages. It is extremely fast, because basically you can approximate at the beginning. You can say that the optimal density corresponds to an average node degree K equal to 3. So you can simply go directly and see as a rule of thumb if these, you can filter directly your networks by using this average node degree. Second, it is inspired by biological concept, that is to say optimal efficiency and sparsity and economy of neural systems. And also is able to emphasize differences between, network differences between different brain states. So if you want to know more details about this work, and there are also this code available in this publication, who just appeared in 2017 in PLOS Computational Biology. Let me acknowledge all the people who gave precious suggestions to the improvement of the method, and also my team in Paris, the Aramis team, and especially the person here who have already talked about brain networks. And thank you very much for your attention.